So thank you very much. Unfortunately, I don't have any experience of interaction with Cyrano de Dominicis, but still it had a huge impact on my, say, little life, because I graduated as an electronic engineer, and then I ran into papers of Virasoro about ultrameticity, of Giorgio Parisi about spin glasses, and then I ran into some papers of de Dominicis, which I couldn't understand at all, completely, and I'm sure you understand what I mean with this, and so I decided I had to take a PhD in physics, because I couldn't stand the fact that I could literally not understand one single. Okay, so today we'd like to talk about auto-equilibrium, the role of auto-equilibrium physics in machine learning and deep learning in particular. And with auto-equilibrium, I mean two things. It can be the behavior of learning process, but also it means the role that subdominant states play in learning. So these are the objects we want to study, and I'm sure you have heard about the success in classification problems obtained through supervised learning with these multi-layer networks. The objects that are studied today can have hundreds of millions of connections, so they're huge, they need a lot of power. And we have been studying this, I mean not the young ones, but the other people, we have been studying this kind of problems in the 90s. Okay? However, we didn't have much success in terms of application, and now what is happening is that those models that we have been studying for quite some time are obtaining a huge success. So let's try to understand what was going on, why we didn't succeed in a sense. Well, the reason also is that there were no data. Anyhow, so essentially, since I have a few minutes, I have to be very short. How does learning take place? Well, you just have a set of examples. You have a mapping input to output, and so at the beginning, all the parameters of the network, the weights, are say random. So at the beginning, the network makes a lot of errors, and you set up an algorithm that minimizes the number of errors. So by sort of gradient descent. Okay, let's say you have a cost function, an energy function, which is the number of errors that the network makes, and then you try to minimize it. And of course, with the system, like this, where these units are highly nonlinear, it's a kind of a very complicated spin glass. You expect to get stuck in some glassy state. And however, this does not happen. And why is it so? Well, the main reason is that there's been an evolutionary process in which all the practitioners have tried thousands and thousands of different algorithms, and they ended up with algorithms that are successful. However, they don't minimize the cost function they are supposed to minimize. They always minimize something else. And if you now try to understand what happens in the space of ground state of the true energy function, so the pure classification problem, we will understand that all these modifications are actually addressing particular type of states which are accessible from a dynamical point of view. So in order to analyze this, I consider the simplest model, which is the binary perceptron, and Bernard was the first probably to study this model. So it's a binary perceptron. So you feed in patterns on the left, and you read out an output which is given by the sign of the sum of wi, xi. Xi is a vector, an input vector. The w's are the weights, the parameters we need to identify, the variables. And you see you have a nonlinear sign function. And we consider a case in which the w's are plus or minus 1. Why are we choosing this model? Because this is the simplest non-convex model we can analyze. Otherwise, we should consider at least, with continuous weight, we should consider at least a network with one hidden layer, and things have become just heavy from an analytical point of view, but it can be done. Okay? So, but this is already enough. So essentially, the problem is the problem of studying the ground state of this spin glass Hamiltonian, in the sense that this is a sum over all examples. This is the output of the network for a given input. This is the desired output. When they coincide, this product is positive, so you have a negative argument of this theta function, so you have 0 and no error. Whereas when this product is negative, so the output is not the desired one, times a negative number, the argument becomes positive, so you have a theta, you count one error. So this function counts the number of errors, right? And so if you massage a little bit this, you will see that it's a typical spin glass problem, okay? So this has been studied many, many years ago, and so it has a critical capacity of 0.83, which means that you can store correctly a number of patterns which is proportional to the number of weights, and the factor is 0.83, and you can study this just by studying when the entropy of the ground state goes to 0, so when all the solutions disappear. Now, a few years ago, Wang and Kabashima studied, using the Franz-Parisi method, studied the typical distance between typical solutions of these ground states, and they found that all these ground states are far apart. So they are all isolated solutions that are typically far apart. Okay, so this is the scenario. So so you have an exponential number of the entropy for alpha smaller than this value. So the entropy is positive. So you have an exponential number of ground states. These ground states are point-like in a sense. In the replica language, Q1 is equal to 1. So the self-overlap is 1. And the distance, the minimum distance between typical solution follows a curve which is always above 0 for any alpha, even for alpha small, even for few patterns, as soon as you start to memorize patterns. So this is the scenario, and so you expect to get stuck and not to find any solution in this problem from using some algorithms, because you have this isolated solution. And indeed, this is what happens if you run a Monte Carlo algorithm, just a simulated annealing. You just get stuck immediately. You don't even minimize a little bit the number of errors. As n increases, you just cannot improve the number of errors for any from random initial conditions. So since we had some results indicating that, in fact, solution can be found, so somehow a paradox, we decided to study a kind of large deviation aspect of this problem. And so we decided to look for the existence of rare, exponentially rare, but very dense regions of solution in this problem. Now, if you do the replica calculation and you take the Parisi parameter m and you change it, you don't find these kind of solutions. So it's really, something which is not captured by the replica method, at least. We didn't find any solution of this type. So we decided to use a slightly different approach. So we defined ab initio a new type of energy function, which is the local entropy, namely the log of the number of solutions of ground state of 0 energy within a certain distance d from some vector w tilde. So essentially we define a cost function which is given a ball of radius d in a high dimensional space, we count how many solutions you have inside this ball. Now, if given this scenario, you would expect this function to be totally trivial, right? Because below the minimum distance, you should have essentially no solution, or one solution. So essentially you should find that this function here is always 0, right? Just one solution. However, we had numerical evidence that this was not the case, so we decided analytically to study this object. And if you do this, well, first, let me tell you, the numerical results that, okay, we can try to run simulated annealing using this function here instead of the traditional energy. And it's interesting because, well, you can estimate this local entropy using the cavity method online somehow, so it can be made efficient. And, you know, quite interestingly, what you observe is that simulated annealing gets stuck in the glassy states, whereas when you try to minimize this local entropy, you immediately, very quickly find very dense states, and that's it. So this is that's just a sanity check that we had to do, but in any case, analytically, what you find is that indeed these dense states exist up to a value of alpha which is close to the critical capacity, about 0.77. So you have regions that are extremely dense. The number of these regions is exponentially smaller than the number of ground states, so you don't see them, they do not dominate the Gibbs measure. However, these regions exist and are very dense. With this I mean that if you compute as a function of the distance the number of nearby ground states, you would observe that the curve overlaps with the binomial coefficient, the log of the binomial coefficient, which means that almost everything is a solution. So very, very flat regions, okay? This was a surprise, and okay, I have to be quick, I'm sorry. So we do believe that this is the fundamental mechanism underlying a lot of the learning processes nowadays, and I'll get back to that. But let me tell you a couple of results before. So one result is that you can write this, this entropy is written in terms of rigid constraints. So this is a constraint on a distance, this counts the number of errors. You can make everything soft, okay, using Lagrange multipliers. And so you can define a local free entropy for this problem, which this is the number of errors the network makes. I use sigma because now I want to use a physics notation instead of W. So this is a constraint that when beta goes to infinity forces the system to go into zero energy ground states. And this gamma is a parameter which is associated to the distance, so it's a Lagrange multiplier enforcing a given distance from this configuration sigma prime. So it's another way of rewriting the same thing. But why am I doing this? Because then you can take this, you define this free entropy, then you want to maximize it, so introduce a fictitious temperature that we call y. And if you take this y integer, then you observe that the measure that focuses on these dense regions is given by an effective model, which is nothing but a real number of y replicas of the original problem coupled to be at a given mutual distance. Okay? So you have now this you can simulate it. You can use it as an algorithm. And in fact, so this is the picture. So you have many models that are forced to be close by. And so now if you compute, you marginalize with respect to all these other variables, what the probability distribution for these variables here coincides with the probability distribution given by the local entropy measure. So it's an algorithmic way of using this idea of local entropy. And these are rare states for the Gibbs measure. And I don't have time to discuss all the algorithms that come by using this technique, but believing that they work. And now I want to say two things. First has to do with quantum mechanics. This replicated system that we define, I'm sure that those of you who have ever played with quantum Monte Carlo immediately recognize that it is essentially the same thing as quantum Monte Carlo, because when you do the Suzuki Throttle decomposition, you get many replicas of the same system, and which are coupled with the ferromagnetic couple, and in the classical limit you send this coupling to infinity so that they coincide on one single model, right? In our case, we have many replicas which are coupled with a centroid, and at the end we want them to coincide. So more or less, they're doing very similar things. I need to be fast. So we decided to analyze this, both analytically and numerically, and okay, we define again this energy function, and now we use the quantum annealing strategy. So we have our discrete variable sigma that now we call sigma z, the z component of the Pauli matrices, and then we introduce a transverse field. And we want to see, given this intuition that they should behave similarly, we suspected that quantum annealing could actually work to solve this problem because of this formal similarity. Okay, and then you do the Suzuki Throttle representation. I'm sure I don't have time, but so this is just very standard. So these are, you replicate many times the same system, and so this is the ferromagnetic coupling between throttle slices, and this gamma depends on the external transverse field. When this transverse field goes to 0, this gamma goes to infinity, which means that all the replicas have to coincide. They are totally coupled, so you have just one system, which is the classical system. Okay? And so this is quantum, the Throttle representation of the quantum system with the transverse field, and this is what we call the robust ensemble, this ensemble of problems that focus on high local entropy regions. So the difference, pictorially look like this. Now you can do two things. You can solve this problem analytically using the replica method, and what you find is in fact that, well, you find this theoretical curve, which is the dotted line here, okay? And then you can actually analyze what happens when you run quantum Monte Carlo, and you observe, there's some technicalities that I don't have time to discuss, and you observe that the curves of the quantum Monte Carlo as the number of slices increases, because we need to send the number of slices to infinity if we really want to claim that the quantum system is going to work, so the quantum adiabatic evolution is going to work. So this is for different values of y, and you see they tend to overlap with the theoretical curve, and so everything seems okay. And if you run on the same system simulated annealing, so classical annealing, well, it always gets stuck, okay? And as you increase the size, it gets stuck higher and higher, so it doesn't, no hope. And in fact, if you look at the shape of the minima found by the quantum annealing compared to the classical annealing, it's very interesting. So this is the most probable energy you observe at a given distance around a local minimum. Okay, and simulated annealing gets stuck in this type of very narrow minima, whereas the quantum annealing always end up in minima that are wide. And they start from the same point just because we subtracted the reference point, but this goes to zero energy, whereas this gets stuck at a higher energy, okay? And similarly, you can show that if you compute using the cavity method, you compute how many other ground states you find close by the solution that you have found, you observe that for the quantum for the solution found through quantum annealing, indeed you end up in a dense region, meaning that you have an exponential number of other solutions around you. Whereas if you do simulated annealing, you always end up in an isolated local minima. So quantum annealing is using this cooperative process to select wide valleys and going down to this rare minima. Now, I'm not an expert, so now these are real-time quantum simulations, and you observe that they perfectly coincide with the theoretical curve. And this is the same, this is as a function of the transverse field. And this is the case in which you take the same quantum Hamiltonian, but you permute the diagonal at random. So you break any geometrical structure, just randomize the energy, put it in some random position, and indeed you find that you get stuck in that case. So really the geometrical structure plays an important role. And okay, so if you look at the minimum gap for this quantum annealing problem, you find that for the original problem, you never have the small gap problem, so the process is going to converge, whereas for the permuted problem, you get very small gaps at a certain point, and so the process slows down. Okay? So the reason for this is a posteriori quite obvious. You have a very dense region of ground state, so the system can delocalize. So the kinetic energy of the quantum system is going to contribute and highlight these regions, okay? And you reach those before having sent the transverse field to zero, so you get stuck there, and you find this solution. So that's my physical interpretation. Now let me, the last bit is something that we just published, is we can consider a model now, a different type of stochasticity. We consider the case in which the W's, again for the binary perceptron, but we have more general results, are just stochastic variables. So essentially you show a pattern to the network, you draw your weights at random, and you observe the output. So it's a stochastic one-step process, okay? And you want to, in the space of the probability distribution, so essentially of these MIs that are continuous variables, you want to study the behavior of this system. Now, this is a stochastic model, so what you have to do is to maximize the likelihood, right? So you want to maximize the probability, given that this is a stochastic process, that the output coincides with the desired output. And so you do this, and notice that even though the W's are discrete, now once you have written the log likelihood for this problem that you want to maximize, you have to maximize in the space of the probability distribution, so it's a continuous space. So you can use a gradient for doing that. So you can use a lot of stuff. But it's more a conceptual problem that I want to address. And what we want to address is that, in fact, this model also ends up in the dense states. So with the other type of fluctuation. Why? Because these are the only consistent ones with respect to a stochastic process. You want to flip, and since it has to be robust with respect to spin flips, it has to be a dense regions. And so even though they're exponentially rare, they end up there. Okay? So the conclusion is this is a natural way to enforce robustness, and it ends up in these high local entropy regions. And we have checked this analytically using the Franz-Parisi approach. And I think this applies to deep neural network in a broader sense that I'll tell you next time. Okay, thank you.